Let's begin by examining 15 factorial. We see that it is the product of all integers from 1 to 15. Now this question is essentially asking us what is the greatest number of 3's that we can factor out of this product. Now notice that we have several 3's hiding among the numbers I've highlighted here. What I mean by that is we can take 6, for example, and rewrite it as 3 times 2. We can take 9 and rewrite it as 3 times 3, 12 as 3 times 4, and 15 as 3 times 5. Notice now that we have a total of 6 3's in this product. So we can factor out these 3's as follows. Notice that 3 to the power of 6 must be a divisor of 15 factorial. And since there are a total of 6 3's in this product, we know then that 6 must be the greatest value of k, such that 3 to the power of k is a divisor. So the answer here is D.
Sid intended to type a 7-digit number, but the 2 3's he meant to type did not appear. What appeared instead was the 5-digit number 52115. How many different 7-digit numbers could Sid have meant to type? So a few interesting things. First of all, notice that these 5 digits have to be in this order. Now the 3's could be breaking them up anywhere. The 3's could be together or apart, but those 5 digits have to maintain that order. So, as always, there's many ways to formulate a counting problem. I think the easiest way is to think about it this way. Let's first of all think of the 7 blank spaces where we're going to put the 7 digits of this number. Well, first, let's place the 3's, and we could place the 3's anywhere, any 2 of the 7 slots. So we could put, say, a 3 here and a 3 here, for example. Once we place the 3's, notice everything else is determined, because then all we're going to do is drop in those 5 digits in order. So in other words, picking 2 slots out of the 7 to place the 3's will determine how many numbers there are. And of course, the way we do that with combinations, that is 7 choose 2. We're picking 2 spots of 7. And of course, what this is 7 factorial over 2 factorial times 7 minus 2, 5 factorial. A little bit of simplifying. That's 7 times 6 times 5 times 4 times 3 times 2 times 1 over 2 times 1 times 5 times 4 times 3 times 2 times 1. Of course, all that cancels, and what we just get is 7 times 6, which is 42, divided by 2, which is 21. Answer choice C.
A class of 10 students would like to elect a president, 1 president, and 2 vice presidents. And no student may hold more than 1 office. In how many different ways can this be done? Let's consider the scenario in which the president is elected first, followed by the election of the 2 vice presidents. Now, 1 president can be elected from 10 people in 10 choose 1 ways, which is 10 ways. And then for each one of these choices for the president, I repeat, for each of these 10 choices for the president, the 2 vice presidents can be elected in 9 choose 2 ways. Why 9? Because the president is no longer eligible to be selected as the vice president. No student may hold multiple offices. So 9 choose 2 is equal to factorial 9 over factorial 9 minus 2 times factorial 2, which is equal to factorial 9 over factorial 7 times factorial 2, and this is equal to factorial 9 is nothing but factorial 7 times 8 times 9. So this is 8 times 9 over factorial 2 is 2. That's 72 over 2. That's 36. So for each choice of the president, there are 36 different ways the 2 vice presidents can be chosen. And therefore, the total number of ways this can be done is 10 times 36, which is 360. Answer choice C. Now, in case you're wondering, would the answer change if we were to choose the two vice presidents first and then the president? Let's go ahead and check that out. So from a class of 10 students, the two vice presidents can be chosen in 10 choose 2 ways, which is factorial 10 over factorial 10 minus 2 times factorial 2. So this is factorial 10 over factorial 8 times factorial 2. Factorial 10 is factorial 8 times 9 times 10. So we can cross them off. This becomes 9 times 10 divided with 2 factorial is 2. So that's 45. 45 ways to choose the vice president. And for each one of these choices, again, the president can be chosen. There are 8 remaining candidates because no student may hold multiple offices. So 8 more candidates remaining, and they're all eligible to be chosen as the president. So that can be done in 8 choose 1 ways, which is 8 ways. And so the total number of ways this can be done is 45 times 8, and that's also equal to 360.
How many different ways can 3 fiction books and 3 non-fiction books be arranged on a row of 6 books on a shelf such that the fiction books are not separated and the non-fiction books are not separated? So first of all, it means that we have to have all the fiction books and then all the non-fiction books, so fiction books on the left and non-fiction on the right, or we could have them in the other arrangement, non-fiction on the left and fiction on the right. So that's the overall arrangement. Now, within fiction, we have 3 fiction books. How many orders can we put those in? Well, we could pick the first choice. We'd get a choice of 3. Once that's picked, for the second choice, we'd have a choice of 2. For the last one, we'd have a choice of 1. So that's 6. So there's 6 different orders for the fiction books. Similarly, 6 different orders for the non-fiction books. Any of the 6 orders with the fiction books could be paired with any of the orders for the non-fiction books. So there are 36 different arrangements when in this overall arrangement with fiction on the left. Well, everything is symmetrical, so again, in non-fiction, there'll be 6 of each of these, there'll be 36, so there'll be 36 here as well. And so 36 here, together, 36 plus 36 is 72. There are 72 arrangements. Answer choice C.
In this question, we have the task of distributing 16 gifts among 4 children. Let's divide this task into 4 stages. The first stage will be to give 4 gifts to the first child. Once we've done that, we'll give 4 gifts to the second child, then 4 gifts to the third child, and so on. Now, in how many ways can we give 4 gifts to the first child? Before we can answer that question, we have to answer an important question. Does the order in which this child receives these 4 gifts matter? In other words, is receiving gifts A, then B, then C, then D different from receiving gifts B, then D, then A, then C? And the answer here is no. The order doesn't make any difference. The child still receives the same 4 gifts. So since order does not matter, we are looking at a combination type question. Okay, so the first stage, we have 16 gifts, and of those 16 gifts, we want to choose 4 of them for the first child. The number of ways to accomplish this is 16 choose 4. Once we've given the first child 4 gifts, there are 12 gifts remaining. And of those 12, we choose 4 of them for the second child. This can be accomplished in 12 choose 4 ways. Now we have 8 gifts remaining, so we can give the third child 4 gifts in 8 choose 4 ways. And finally, with 4 gifts remaining, we can give the last child 4 gifts in 4 choose 4 ways. So the total number of ways to accomplish the entire task will be the product of each individual stage. At this point, we want to evaluate these values. So we'll use our formula for combinations. And let's apply that formula here to get the following product. At this point, we can do some simplifying. We can cross out our 12 factorials and our 8 factorials to get the following. And since the denominator features 4 factorial times itself 4 times, we can rewrite that as 4 factorial to the power of 4. And we can see that this answer is exactly the same as answer choice C.